Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the Uni of Adelaide. It's semester 1, 2024, and this is a revision seminar for Algebra 2. And yeah, here we go. All right. Okay. Well, let me just do the first question. I guess so the specific question for those who weren't here when it was asked, i.e. you watching on the video, is how do you tell if particular groups are isomorphic or not? Because it keeps coming up. So we'll do a couple of examples. I just want to talk through some ideas. It's quite similar to telling if vectors are linearly independent in the sense, not really, but just in the sense that there is a definition of the thing, and then there are a few ways to tell that aren't directly using the definition. So we do need the definition, and you can always use the definition if all else fails. And the definition of being isomorphic, as far as I'm aware, and I'm just going to check that the lecturer agrees with me. Groups G1, and so this is a definition, under that operation, and G2 under that operation. Are isomorphic when there is a one-to-one and onto map phi, which sends G1 to G2, such that for all elements G and H in the first group, phi of G times H, or whatever the operation is phi of G. That's the definition of being isomorphic. So if you would like to show that groups are isomorphic via the definition, then you must make a function that goes from one to the other that preserves the group operation. That if you do the group operation in G1 first, before doing phi, it's the same as doing the group operation in G2 after doing phi. And so it's really important to point out at this time, I know I'm just going to point it out that these two things here, they are in G2. Yeah. And this operation here is also the operation in G2. Whereas this operation is in G1. Yeah. So if you do, yeah. Most groups, people like to write the operation as multiplication, but there are some addition ones. So you've got to keep track of which one you're in if it switches its symbol. Okay. So that's the definition. And if you're not sure, that is the surefire absolute way of telling if two groups are isomorphic, is to set up that isomorphism. So I will say something important about that, which is if your groups are finite, then the only way for them to be isomorphic is to be the same size. Because the only way for finite sets to have a one-to-one and onto map between them is for them to be the same size. So just a note. So the first thing we can get out of this is that if G1 and G2 are finite, they can't be isomorphic if the size of G1 is not the size of G2. That's how we write the size of a group, isn't it? Yeah.
Yeah.
Oh, order. Fancy. Right. If they are the same size, there's no guarantee. There's no guarantee they're isomorphic if they're the same size. But it is possible, at least. So this is a way of telling that things aren't isomorphic. If they're different sizes, they cannot be isomorphic. And that goes even if they're not finite. If one of them's finite and the other one's infinite, then they can't be isomorphic. So that's the first step. Okay. Give me a second. So some things that are definitely true are that phi of the identity in the first group will work out to be the identity in the second group. But that just tells you if your phi is an isomorphism, not that you don't have an isomorphism. Like, not that there can't be an isomorphism. So when you're trying to think of a good phi, then it has to make the identity turn into the identity, like the identity in one and turn into the identity in the other. And it should preserve inversion as well. And I guess it preserves powers too. Powers in the sense of if this is multiplication, doing a whole lot of G's at once here. Just be careful with addition, that doing the addition multiple times you don't write it as a power. You write it as n times thing. So yeah. So that's that. And none of those are ways of telling whether the function you're thinking of is an isomorphism or not, but it doesn't tell you whether there is an isomorphism. It just told you that the one you've thought of is a good one or not a good one. Okay, so, but what isomorphism does is it tells you the two groups are the same in structure. So if you made a great big multiplication table, you should be able to write the elements in an order in such a way that the multiplication tables look the same. And also, there's other things that are true about groups that are isomorphic. It will preserve all the subgroups too. So note, have like all the same size subgroups, and they have all the same orders for their elements. So if you find an element in one group that has order, say 6, and there's no element in the other group with order 6, they can't be isomorphic. So if G1 has an element or subgroup of order k, but G2 doesn't, they can't be isomorphic. That's an important point. And it is one of the ways that people argue that groups aren't isomorphic by happening to find an element in one that has an order that doesn't exist in the other. Right. That's all I can think of at this time. Correct. I'm going to just say that there. It has to also have to have the same number of elements of each order. So e.g., if G1 had 2 elements of order 4, but G2 had 4 elements of order 4, they can't be isomorphic. Yeah. Yeah. It would break the one-to-oneness of the map. Because once you did phi of element to the power of 3, in one of those, like in G1, that's a different element, but in G2, it's just the same element as another one, and so your function's not one-to-one anymore. Yeah, so something like that. The thing you thought was an isomorphism can't be. So they are things you're kind of allowed to say, I think. If someone just says, give a reason, you have to give a formal proof. You would say, suppose phi is an isomorphism between them and consider this element and do some stuff. So let's do some proper examples, hey? What's the symbol for isomorphism? 1 bar and a curly bar twiddle? Double in the note in these notes. So sometimes it's just 1. I don't think so. Okay. Klein 4 group is not isomorphic to Z4. And the reason I know this is that every element of the Klein 4 group has order 2, except the identity, which has order 1. But V4 has 3 elements of order 2. Because it's got 180-degree rotation, which has order 2. You do it twice, you go back to the beginning. It's got reflection this way and reflection this way. They all have order 2. But Z4 has only 1 element of order 2, which is 2. But also it has 2 elements of order 4, because 1 and 1 plus 1 and 1 plus 1 plus 1 and 0, that's the span of 1. Sorry, the subgroup generated by 1, and that has order 4, and the Klein 4 group doesn't have any elements of order 4. It's 2. And the elements here are 1 and 3 that have order 4. So yeah, Z4 is a cyclic group. It's generated by 1. V4 doesn't have any elements of order 4. Has 0 elements of order 4. Yeah. And you can always make a group all of whose elements have order 2. That's always possible. Pretty sure. Could be wrong. No, you can't. I was wrong. groups don't work that way because subgroups have to divide the order of the group. So an odd-sized group can't have elements of order 2. Yay, okay. I am pretty sure that if your group has prime order, there's only one. Pretty sure that's a theorem because it can't have any subgroups. And so its list of subgroups is just itself and hence must be cyclic. And all cyclic groups of the same size are isomorphic. That's a theorem. Yeah. But yeah, definitely here, these two cannot be isomorphic because this one has an element of order 4 and that one doesn't. So I'm sure about that. But your other example is, is R star under times isomorphic to R under plus, was it? And those are infinite groups. So order is going to be a tricky ass one to talk about. Now, everything in R has order 0. Like it's impossible to keep adding things to get the same thing over and over and get back to 0. Like the identity here is 0 here, and the identity here is 1 here. And so to do the order of an element, you would have to keep adding it to itself to get back to 0. And so there is no way to do that. Everything has like order 0. And whereas in this one, it's the same. Everything has order, oh no, -1 has order 2. Because -1 times -1 is 1. So all elements here have order 0. Also, like given any number in R, given any x in R, the subgroup generated by x is infinite, except 0. Because if you keep adding x to itself, you'll never get, and you can do minus x when you do the generated one. You have to put the inverses in as well. But, this is dot, 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 minus 3x, minus 2x, minus x, 0x, 2x, etc. That's infinite. Whereas over here, the subgroup generated by -1 has 1 and -1 and -1 times -1, damn it. So there's -1 and -1 times -1 is 1. And so therefore the subgroup generated by -1 contains -1 and 1. Not infinite. So you can't map -1 to anything over here. Like, well, none of these can map over to -1 because these do not have finite they don't not generate finite subgroups. So I think they can't be isomorphic. Is that the solution says? Is this how they did it or did they do it elsewhere? As an element of order 2, but R can't be 0, otherwise 5 minus 1 would be another. Yeah, so I'm just going to say that. Suppose phi, which sends R star to R, is an isomorphism. Then phi minus 1 times minus 1 would be 5 minus 1 plus 5 minus 1. Because multiplication is the operation here and addition is the operation here. And that would be phi of 1, which would be 2 times 5 minus 1. And this would be 0. And that would only be true if 5 minus 1 was 0. This is a whole different way of doing the argument. Yeah, which it cannot be true because phi of 1 is 0 and it's a one-to-one function. But there's another way of doing it, which is like, therefore 5 minus 1 has order 2, but there are no elements of order 2 in. So you could do it that way. This way is slightly dodgy because I'm borrowing some things about the way addition works and multiplication, how it's related to multiplication in R, which if I didn't know anything about the groups, you couldn't use. So I should probably, the safest thing is actually to say that 5 minus 1 has order 2, but nothing has order 2. Yeah. Yeah, so I should probably say, so 5 minus 1 has order 2, which is not possible in R plus. Yeah. Okay. Contradiction. There is no isomorphism. Well, that turned out nice. Yay. Why minus 1 just occurred to me? I was just thinking about, like, it seemed to work well in the other one to think of the subgroups generated by each of the elements. And I was wondering about subgroups generated by, and all of these are infinite, and going, can I think of one that's finite over here? Are there any numbers that when I multiply them by themselves, I get back to 1? And there is one. Yeah. There's exactly one. Which means that C star dot is not isomorphic to C star plus either, for the same reason. That C star dot has lots of elements of small order. Okay. Someone's having trouble connecting. Okay. I think that's the main thing. But if you want to prove that things are isomorphic, the only way is to come up with a phi. We'll make that point. The only way to be sure two groups are isomorphic is to describe a phi, like an isomorphism. Explicitly, you have to say explicitly how to get from what the output is, basically. Yeah. There are some other theorems, I'm sure, but that's about it. Okay. Well, That's cool. I might as well just pop that in minutes. No, who knows what's going to happen today. Okay. Right. Well, my other list had dual spaces and stuff and intuition thereof. I might just start there. I'm not 100% sure on all the details here, but I can be sure of a few things. So dual spaces seem like such an innocent idea, but they seem to come up all the time. Don't quite understand why, but I do know some things about them. So if you've got a vector space over a field, does your lecturer use like a blackboard bold F for the generic field? Oh, damn it, I lost my focus. That's okay. Then it is if it's finite, you can definitely find a basis so that everything can be written in terms of the basis with all these coefficients, and you can use those coefficients as coordinates. So that's a useful thing to know. If B is finite dimensional, then there's a basis V1 up to V something, let us call it R, that's tradition, so that for every V in V, V is something times V1 plus something, all the way up to something times VR plus some A1 up to AR in F. Okay. That's, that's the definition of a basis. A basis doesn't just have that property. It's actually, there's a unique set of A1 up to AR for every V. Each V has only one way to do that, and every way to do that produces a different V. That's they're unique. But you could think of V as the coordinates A1 up to AR if you wanted. Traditionally written as a column probably, but it doesn't matter. If you want to use matrices, you have to write it as a column, probably, traditionally. Yeah. So you think of those coefficients of the basis as the coordinates of V. Not obviously, but if you choose a different basis, you'll get different coordinates. And Rn already looks like this. So that's great. But other vector spaces do not already look like that, but they do usually have a natural basis that goes with how you write them in the first place. So the polynomials, for example, have a basis already, which is 1 at x and x squared and whatever, because you already write them as a combination of those. And so that's the natural basis. I don't think it's officially called the standard basis, but anyway. You think of V as being equal to that thing, so that the coefficients have become coordinates. All right. Well, you know how in Rn you can write vectors as either rows or columns. And when you do a row times a column, it does the dot product. I'm just going to do this and write it as a column for reasons in a second. Well, is there like a fundamental difference between row vectors and column vectors? I mean, then no, right, because they're not. But also yes. Because we're really in Maths 1 A and B, we're really quite forceful about the fact that vectors really should be columns. In which case, like, what is a row vector then? Well, what it is a function that if you multiply it by a column vector, you get a number. Well, they're like descriptions of functions. Where you go like f of x1 up to xr is equal to, you know, b1 br times x1 up to xr, and what you get is a number, right? That's what happened. Here we go. In R, let me use n because I don't like to say RR. That's ridiculous. In Rn, you got row vectors, their description of functions, and what they do is this. So, since linear algebra in this course is fundamentally more abstract, the whole point is to find other things that aren't Rn that still behave the same way. We need a way of turning that into a thing that doesn't require coordinates to describe it necessarily, though you will be able to create coordinates if you want to. But that's the idea. So we're going to turn that into something else. And what we're going to do is we're going to take this idea, the functions. So what we have is functions that take an input from Rn and produce a number. And if we keep the b's the same, it will do something to every other vector, and each one will produce a number of its own. Pardon me, they won't all produce different numbers because there's not enough space to do that, but that's how it's going to work. And so what we define is we say that V star, which is the dual space to V, is set of linear transformations phi which send V to the field. So not just any functions. Because we are officially multiplying by a matrix, that means that we can expand it out over plus. And we can bring out constants out the front, which is how linear transformations work. And the official name for these things is linear functionals. Pretty sure that's what they're called, right? I did go here in my page. Linear functionals. There's a word for you. But that's what they are, the set of linear transformations that send V to F. And we're borrowing our idea that row vectors are linear functions from Rn to R. So just like right. So that is what the dual space is. And it turns out that the dual space is isomorphic to the original space. Just gonna check that. Definitely works if it's finite. Well, maybe the dual space isn't isomorphic to the original space, but the dual space is definitely, if you do the dual twice, you'll definitely get something that's isomorphic back to the original. No, they are isomorphic as long as it's finite dimensional. So here we go. If there's a theorem and the theorem is 2.28, and a theorem 2.28 says more than this, but part of what theorem 2. This is the definition here. There's a theorem, and part of it says is that if V has a finite basis, like is finite dimensional, then V star is isomorphic to V. Is there a thing for isomorphism for vector spaces? Did you talk about that? But we do actually, in fact, have that terminology for vector spaces. Okay, cool. So that means they're isomorphic as groups under addition, but also the isomorphism also preserves scalar multiplication. I mean, it just means there's a linear transformation from one to the other, but that is one to one and onto. But if V is finite dimensional, then V star is isomorphic to V, and that is not unexpected because we designed it specially to be the same as the relationship between row vectors and column vectors. That's what we designed it to do, and row vectors and column vectors really not that different from each other. Like they look the same, just this way around. So you do not need to, like this is what it's supposed to do. Like we expected. There's row versus column vectors, right? That's what we expected it to do, and therefore it is good that it did that thing. A lot of the abstract algebra stuff is trying to say, here's some stuff that we saw that we're familiar with. We're going to try and make it more general so we can apply it to more things. So it still has, whatever definition we have has to still match with what we expect it to do. Okay, so V is finite dimensional. This is true. I'm just going to take a little pause here. Is that even if it wasn't finite dimensional, you can still come up with things. I just need a little example here while we're at it. There is a more to theorem 2.28, but the big upshot of it says that if it's finite dimensional, V is the same as V star, just in a different orientation. Well, at least that's how I think of it. So just as an example, we should do this with vector spaces that aren't Rn. And the classic vector space that isn't Rn is the polynomials. That's the usual one that most people pick. Now, what's the notation for the polynomials? Rx2 or something? Yep. With real coefficients and degree up to 2. Okay. Now these aren't vectors, like they in the sense of, I mean, they are vectors because they are a vector space. They aren't strings of coordinates. And they do things that strings of coordinates don't do, such as multiply by each other. I mean, they don't, because if you multiply two of them, you don't get something in R2X. But they do things. So yeah. So we're going to say that P of X, I'm just going to give a random one. Something like that. Maybe I'll do a plus. Yeah, whatever. These are elements of R2X. They're both polynomials with real coefficients. Officially, I could put pi or √7 in any of these spots. sure. There's such a thing as Q2X as well, because Q is a field. But this is the most common one. And you could imagine this as 1, 3, -1 if you wanted to use coordinates, right? Or if you wanted 1, 3, -1, I guess. And this one would be 5, 0, 8, right? If you wanted. Just to bear with it. And that's using a basis of 1 and x squared. But you can use other bases. Cool. So linear functionals are anything that will turn this into a single number in such a way that if I add these together, I get the same first and then do the function. I'll get the same answer as if I did the function and then added them. And one of the classic linear functionals is the one that when you sub in a specific number. So I can have that phi of p of x is p of, say, I don't know, 2. That's a perfectly good linear functional. Phi starts in R2x and produces a real number. That's the first thing it needs to do. And also phi of P1 plus P2 is phi is this function but with 2 subbed in, right? There's a word for this. You actually put a like that. That is the notation for sub that in. I don't know if you've seen it before. It's like a ceiling symbol with a 2 at the bottom. Which is phi of P1 plus phi of P2. It really is a linear functional. It's surprising. It doesn't feel right. And the other thing to be a linear function is it has to have you have to be able to multiply by a constant and the same thing will happen. And it does. So it really is a linear functional. And in fact, all of the they call them evaluation. All of the evaluation functions are linear functionals. And in fact, you can make a basis for V star, if this is what V is. You can make a basis for V star out of entirely these things. It's pretty cool. And there are other linear functionals, like, but I can't remember how to do them. But anyway. Okay. But it is useful to know that that is like when you're asking for intuition for things, it's really useful to find things that break your current intuition so that you can add new things to your intuition. Like when you first own a cat, you have some intuitions about how they should behave and then they don't. And so you have to add, as you live with them, you start to get used to the new things they do that you didn't expect. And that's the same with linear algebra, like general linear algebra. Okay, cool. Anyway, that's my favorite example of a linear functional that doesn't feel like multiplying a row vector by a column vector. Not at all. But it is. There is another kind of linear functional that I would that does bear mentioning, which is I'm going to call it psi of p of x. I'm going to call it the integral from 0 to 1 of p of x dx. That's a perfectly good thing that takes a polynomial and produces a number. So that's a polynomial here. This is a number. And if you do integration If you add and then integrate, you'll get the same answer as if you integrate and then add. That's how integration works. So also a linear functional. So any function that always does the same definite integral of everything you put into it is a linear functional in this vector space, which is kind of weird and cool. Yep, both of those linear functionals are in the same vector space. So both phi and psi are in V star because they are both linear functionals from R2x to R. So they look different, but they are the same kind of thing. Yeah, because they're doing the same job, which is puzzling, right? But one of the points of linear algebra is that there will be things that don't look like you expect that still behave the same way. And so you can borrow the theorems and apply them to these things that look different to what you expect, but still follow the same structure. Yeah. Okay. So I need to keep track of my page numbering. Well, that page isn't even got anything on it. 5. So the rest of that theorem theorem 2.28 goes, if V1 up to V R, well, no, it's R now, is a basis for V, then it is possible to find a basis for V star with the same number of vectors in it, well, same number of linear functionals in it. Then you can create a matching basis for V star in such a way that the number that phi produces is 1 if you sub in the matching V. So that phi 1, when you sub in the basis into phi 1, only V1 produces a 1 and all the other ones produce a 0. And when you sub in the basis into phi 2, only phi 2 produces a 1 and all the other ones produce a 0. And so on. And in the notes, they write that as phi I of Vj is delta Ij. Because of course they do. But that's short for this. And that's enough. Like, knowing what a linear transformation does to a basis is enough to know what linear transformation does to everything. Yeah, and this is called the dual basis to V1 up to VR. Yep. And conversely, if you had a basis for V star, then you could find a matching basis in V that did this same trick. That would be okay too. Yeah. That's the theorem. And therefore they're isomorphic because their isomorphism turns V1 into phi1 and V2 into phi2. And then it turns some linear combination of these into the matching linear combination of these because of how linear transformations work. How do you feel about that? What this means is in Rn, the dual basis to, all right, let's just see what this looks like. So in R3, for example, that's my V. My V is going to be R3, which is made of things like this, A, B, C. And it has a standard basis you know, 1, 0, 0, and 0, 1, 0, and 0, 0, 1. Then the dual basis would be 1, 0, 0, 0, 1, 0. Well, so that's E1, E2, E3. I don't know if there's a standard name for it, but the dual basis would be phi1, which phi1 of x would be 1, 0, 0 times x. And phi2 of x is 0, 1, 0 times x. And phi3 of x is 0, 0, 1 times x. Cool. But what if I picked a different basis? Oh, now I have to make it, oh, damn you, David. There's my basis. They are definitely linearly independent. This one's not a multiple of that one, and this is not a combination of those two. Do you have that theorem in this course? The theorem that says that a list of linearly independent a list of vectors is linearly independent if each of them is not a linear combination of the ones before it in the list. That's my favorite way to tell if things are independent. And you must have independence in this. There you go. The non-zero vectors V1 up to Vm are linearly independent if and only if at least one vector can be expressed as a linear combination of the ones the preceding vectors, the ones before it in the list. So if you don't have to do all possible linear, because like officially they're linearly independent when none of them is a linear combination of any of the others, but you actually only need each of them to not be a linear combination of the ones before it, which is a nice way of coming up with a list of random vectors that are definitely independent by going, well, I'll pick one, then I'll pick one that's not a multiple of that, and I'll pick one that's not a combination of those two. And a very easy way to make something not a combination of two other things is to pick a combination and then change one coordinate. So yeah, anyway, that's welcome to the mind of a lecturer who's trying to write assignment questions. So this is a basis. It must be possible to find a dual basis that goes with this. So I need something that when I run this through the linear transformation, it produces 1 for this and 0 for this, and 0 for this. And that will be the dual basis vector, linear functional that goes with V1. And we need something that has 0 for this and 1 for this and 0 for this. So I need, so phi1 of x will be some row vector B1 times x, right? That is definitely true. All, that's how it works. All linear transformations that go from R somewhere to us R somewhere else can be written using matrices. And so I need B1 times this to be 1, and B1 times this to be 0, and B1 times this to be 1, to be 0. So I need B1 times 1, 2, 0, 1, 3, 0, 1, 1, 1 to be 1, 0, 0. I need that to be true, right? And similarly, I'm going to need B2 times these three things to be 0, 1, 0. And B3 times this whole thing has to be 0, 0, 1. So if I make a matrix that has these three as its rows, and I multiply it by this matrix, it will produce a matrix that has these three as its rows. And therefore, nothing up my sleeves, the matrix that has B1 in the first row and B2 in the second row and B3 in the third row times this one that has the vectors as columns will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And therefore, this matrix is the inverse of that matrix. Is that not cool? So your dual basis, if you take your original basis and find the inverse, then your dual basis is the rows of the inverse. That's what the dual basis is doing. It's the rows of the inverse matrix to your original basis, which is really cool. It's a nice thing to know, I think. Does that help at all? Good. Yeah, so I'm just going to write that down in words. Rows of the inverse of the matrix with the original basis as columns. Never ceases to amaze me the sorts of things like that happen. Yeah, that's just such a neat little magic trick. Okay, one more example. Do you mind, are you okay with me continuing this and to really get a handle on this thing? Okay, good. Now I know that this has a standard, a natural basis. I'll call it P1 and P2 and P3. It's weird, sorry. It must have a dual basis. So there must be some linear functionals that when I do them to these three functions, produce 1, 0, 1 for this one and 0 for these, 0 for this one and 1 for each of these, and 1, 0 for 1 for that one and 0 for these. So like each of them is 1 and the other ones are 0. So I do know one of them, subbing in 0 will make these 0 and that one 1. But no other subbing in one is going to work. So I do know one of them. So I do know that phi 1 in this case of p of x is going to be p of 0, because phi 1 of p1 is p1 of 0, which is 1, because p1 is always 1, and phi 1 of p2 is p2 of 0, which is 0, and phi 1 of p3 is p3 of 0, which is 0 squared, which is 0. And so this is definitely the dual basis vector, dual basis linear functional that goes with this basis polynomial. Definitely true. Sweet. But no other subbing in is going to work because they're always going to have a 1 in this spot. So I'm going to have to do something else. I do not like it, Sam, I am. Integrals aren't going to work either. The integral of 1 from anywhere to anywhere else is never 0. Curses. Oh. Oh, so cool. Differentiate it and then sub in 0. Because derivatives are linear transformations from v to v. And so, that's so cool. That's ridiculous. That's so silly. So phi 2 of p of x is going to be p dashed of 0. Oh, that's so stupid, but cool. I was going to mention, the reason I'm kicking myself is I was going to mention earlier that differentiating and then subbing in would also be a linear functional, because derivatives expand out over plus and times and multiplying by a constant as well. See, look, phi 2 of p1 is p1 dashed of 0, and p1 dashed is always 0, and phi 2 of p2 is p2 dashed of 0, and p2 dashed is 1. P2 is x. No. It's going to have to be half. It's not. No, 0 is okay. No, it's okay. Phi 3 of p3 would be p3 dashed of 0, which would be 2 times 0, which is still 0, so we're okay. But the last one is not going to be just p double dashed. It's going to have to be half of p double dashed. And phi 3 of px is going to have to be half of p double dashed 0. And the reason is that p double dashed for p3 is 2, not 1. Ah, yes. So then phi 3 of p1 is 0, and phi 3 of p2 is 0, and phi 3 of p3 is p3 double dashed of 0, which is a half times 2, which is 1. Oh, that's so cool. Okay, so I would put that in an exam if I was a lecturer. Or maybe I wouldn't. I talk a lot about lecturers who choose assignment questions based on coolness rather than tractability. But now you know that differentiation and then subbing in, or differentiation and then integrating, doing a definite integral, is, yeah. And actually, yes, you're right. Subbing in two numbers and subtracting them is also a linear functional. Anyway, sorry about that. I'm getting overwhelmed. So that is the dual basis. So these three things, phi 1, and phi 2 and phi 3 is the dual basis to 1x and x squared. Yeah, and this one was subbing in 0, and this one was p dash 0, and this one was half of p dashed of 0. Oh, which is exactly p double dashed of 0, which is so like making a Taylor series. Because I reckon if we were in R3, this next one would be 1/6 of P triple dashed, and then the next one would be 1/24th. Like it would be, it's exactly the Taylor series. Oh, that's just the coolest thing. So the coefficients of your Taylor series, the act of finding the coefficient for your Taylor series that goes with that spot is the linear functional what? Is the linear functional. Wow. That's remarkable. I'm blown away. I've never seen that before. That was fun. Okay. Huh. Do you know the interesting thing about that means that if this is a basis for the linear functionals from R2x to R, then that means that I can write any integral as a combination of these acts. If I have the integral from 0 to 1 of p of x dx, I can do the integral from 0 to 1 of any polynomial by doing the correct combination of these things, which I think is amazing. Yeah. Okay. So the last thing about linear functionals, like the dual space, is that there's a theorem after the theorem that I was saying before, and that theorem is that if you wanted to write something in V as a linear combination of the basis, and you had the dual basis, it would tell you the correct coefficients. So you know that if V is in V and V1 up to VR is a basis for V, then V is something V1 plus all the way up to something VR, right? That's true. That's what a basis is for. So you know that's true. And it turns out that if you've got a dual basis, then it tells you what these coefficients are. If phi1 up to phi r is the matching dual basis, that's just in my head, it's called a matching dual basis, but that's not the official title. It's the dual basis to V1 up to VR. Then the coefficients are phi1 up to phi r of V. Then A1 is phi1 of V, and A2 is phi2 of V, and A3 is phi, and so on, right? I should probably just put dots, right? So to get the right coefficients here, do all of these functionals on V, and it gives you the correct coefficients, which is super cool. And that's exactly why this worked out to be the process that finds the Taylor series coefficients, because that is how you find the correct coefficients to rewrite something as a polynomial. Feel deep connection to that theorem. There is more to this theorem. You can do this backwards. If you would like to write a linear functional as a combination of your dual basis, then you can do it as well. So also, if phi is anything in V star, then you know that phi is something times phi1 plus all the way up to something times phi r. You know that's true. And the correct coefficients are that B1 is phi of V1, all the way up to BR is phi of VR. So in this one, if we want to write a vector as a combination of the basis, then the correct coefficients are these functions acted on V. If you want to write a function as a combination of the functional basis, then the correct coefficients are the function acted on these vectors. So you either act all the functions on the single vector, or the function you're thinking of on all the vectors, and it works out, which is just sweet because that means I can do the integral from 0 to 1 and figure out what that is as a combination of my other things. I'm going to do it now. This is so cool. Okay. So phi of P of X is the integral from 0 to 1 of P of X dx. Right? And so I would like to write, and phi 1 of P of X was P of 0, and phi 2 of P of X was P dashed of 0, and phi 3 of P of X was P half of P double dashed of 0. Cool, 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 cool. If I want to write this as a linear combination of these, and just note, that went with this. They went with this basis. This dual basis went with this original basis. So the theorem says that if I want to write this linear functional as a combination of these three, then all I have to do is figure out what my linear functional does to the irregular basis, and it will do the trick. Need more space. Yeah. So phi of 1 is the integral from 0 to 1 of 1 dx, which is 1. And phi of x is the integral from 0 to 1 of x dx. I'm just going to do that. So half of x, 0 to 1, which is a half. And phi of x squared is the integral from 0 to 1 of x squared dx, which is a third of x cubed from 0 to 1, which is a third. And therefore, phi of any function, so therefore phi, just to be clear, phi is therefore 1 times phi 1 and a half times phi 2 and a third times phi 3. These are the correct coefficients. And what that means is the integral of any polynomial of degree up to 2 from 0 to 1 is therefore phi 1 of P of X, which is P of 0, plus a half of P dashed of 0, plus a sixth of P double, like a third times a half of P double dashed of 0. So there you go. If you would like to find the integral of any degree up to 2 polynomial from 0 to 1, the answer will be this, which is just silly, but deeply cool. I want to try it. Right. So the integral from 0 to 1 of like 3 minus 5x plus a third of x squared dx should be this when you sub in 0, which is 3, plus a half of the derivative of this when you sub in 0, and the derivative of this is minus 5 plus 2/3, it's just minus 5, plus a sixth of the second derivative of this when you sub in 0, and the second derivative of this will be 2/3. Which makes perfect sense, because this is exactly what you get when you integrate it, like the third, oh wow. But anyway, So that is the answer. That is great. I'm whatevs. This is apparently 3 minus 5 over 2 plus a ninth. That is, wow. And I can see the half here. Of course it's a half because that's what happens when you integrate x. And of course this one has a, yeah, of course it has a 6 because, yep. Because when you integrate this, I'm surprised that's not a third. But it will be a ninth when I integrate this because it'll go, so it all works out. Oh, no, it's a 6 because the 2 that's part of the 6 cancels with the 2 that comes down when you differentiate. Oh. It's just stupid. But I love it. I love it so much. This is the thing that I like about algebra. It's just, in many ways, to me, it just feels silly, but it's just a good silly. It's like the Emperor's New Groove or something. Like it's the Emperor's New Groove of pure maths. That's how it feels to me. I'm sure it doesn't feel that way when you try and do an exam on it, but anyway. Yeah. And so that's the last theorem in that section about dual spaces. Other than the fact that if you do the dual of the dual space, it's sort of isomorphic to the original. But then I don't want to go there. Yeah. But I really like seeing what happens to these things. Yeah. Anyway, that's some fun ass stuff. So I think we've sucked all the juice out of dual spaces. Any questions before I move on? Cool. Well, now I have to pick something else to talk about. Where's my list? Quotient spaces, bilinear forms, or tensors. Quotient space. All right, let's find a bit of the notes that talks about them. Truth. Bilinear forms come in both inner products and tensors. Eigenthings. Quotient spaces. All right, let's look at it. Sure. It's the same as quotient groups. So if W is a subspace of V, a vector space, then since V is a group and so is W, then that implies that W is a subgroup of V when you're thinking only about the addition. Well, and to be a subspace, it has to be not empty and closed under addition and scalar multiplication, right? Just a second. W is not empty. That's rule number 0. And Rule number one is that it's closed under, your lecturer calls rule number one the one where it's closed under addition, but I call rule number one the one where it's closed under scalar multiplication, because it only uses one vector. If W is in big W and A is in the field, then AW is in big W. And rule number two is if W and U are in big W, then W plus U is in W. That's the definition of being a subspace, which is only slightly different from the definition of being a subspace that you saw in Maths 1b. In Maths 1b, this one says the zero vector is in W. And you're allowed to use that as your rule if you want. Well, theoretically, a mathematician could use that as their rule for being a subspace, because if a subspace does have a vector in it at all, then this rule will cause it to have the zero vector in it. But now you don't have to prove it has the zero vector in it. You just have to have a vector in it. Yeah. Okay, so back again. So this rule here being closed under addition, if you're looking at just the addition, and this, then that causes it to be a subgroup under addition. The W plus is a subgroup of V plus. Which means it has a quotient group. And the quotient group is all of the cosets. That's how you write a quotient group, right? It's the set of all the cosets. Yep. And it turns out that that's enough. And the scalar multiplication thing works fine. So turns out is okay. So still a vector space. Cool. But that's fine. That's all. That's very extremely abstract. But what is the coset of a subspace? What does it look like? If you're familiar with what subspaces look like, then what is that? So suppose that V is R3 and W is the plane. We know. Do they use angle brackets for span in this course? Like for span in subspaces? Back in Maths 1b, we use the word span. Oh, no, they write the word, oh no, they have all three. Span S or lin S or angle bracket S. Okay. V here is equal to R3. And then W is going to be the span of a couple of vectors. these two vectors. So they're all the vectors, and i.e. all vectors with y equals 0. Which is the xz plane. So what do the cosets of the xz plane look like? So there's a kind of a picture of the xz plane, that's W there. If I add a vector, that's the same vector to every point in this plane, I will get this plane. Parallel to the original. And so the cosets are going to be, do a slightly different color. Really should have used the lightest color at the back, but it's too late now. The cosets are going to be all the planes that are parallel to this plane. That's what the cosets are. So the cosets are the planes parallel to this. And like any vector in this green plane, like for example, any vector in this yellow plane, plus any vector in this blue plane will make any vector in some other plane over here. And you'll always fall into the same planes. Like any vector in the green plane plus any vector in the yellow plane will produce something that's in W because they're equally spaced on either side. And so in some senses, this coset is minus this coset. And so the way that these planes work is that in terms of the structure of them, they add together in exactly the same way as just the points on the y-axis, because that controls which plane I'm in. Now, I can do angled vectors to get from one to the other, but I only need one representative vector that adds to this to get this coset. And I can just choose the vectors that are on the y-axis. And so the structure as just the y-axis. And you will see that we had a plane and the cosets of that plane behave like a line. And so that's a dimension 2 plus a dimension 1, which is dimension 3, which is the dimension we're in. And so there is a theorem that says the dimension of the subspace plus the dimension of the quotient space is the dimension of the big space. So if W was just a line, then its quotient spaces, then all of its cosets would also be lines, but you would have a plane's worth of lines, because you could just figure out which line you had by where it met, like the XY plane or something. And this one we could figure out which plane I have by where it met the y-axis. I could also figure out which plane it was by where it met any line, and that would still work the same way, but all lines through the origin are isomorphic. So that's what quotient spaces are doing. And that's about it. And I don't really know what else there is, but that is a picture of what a quotient space is. And I just really do also want to draw the quotient space of the W. Capital U it is then. U is the span of just one vector. One, 1, 0, say. That's this vector here that lives inside the XY plane. And so we get that W is that U is this line. That's 110. This is U. And then what the quotient, what the what the cosets are all the lines that are parallel to this line everywhere through the entire space. And there's a plane's worth of them, because if I pick any plane that doesn't contain that line, then they all meet that plane in a different point. And so there's a plane worth of them. And so that's why the dimension of so the dimension of V on W is 2, because there's a plane's worth of them. Yeah. And this is the algebra that's based on the idea that if you want to solve a homogeneous linear equation, you want to solve a non-homogeneous linear equation, you solve the homogeneous one, which gives you a subspace, and then add one vector to the answer to get all the rest of all the correct answers. What you're making is a coset. Yeah. So, yeah. There you go. So that's what that matches up with. This concept of a quotient space is the thing that theorem of homogeneous solution plus particular solution is based on. Yeah. Because any vector that goes from this line to that line will do the trick to cause that coset. Yeah. Well, this line to that line. I have 4 minutes left. I already had page 13. You see, you can tell I'm tiring. All right. Well, the other thing was bilinear forms and various other things. Bear with me. So once inner products was defined, they were able to describe the Gram-Schmidt process, which we all love. I do. No, I mean, I don't want to do it, but I love that it's there. There's only one way to find an orthonormal basis in fairyland, and it is through the Gram-Schmidt process. So I guess it is now time in the last minute to say any questions about what we've done so far? Well, you're most welcome. Give me 1 second. Surely there was a thing that said that you could create a bilinear form you could create an inner product from a bilinear form. A positive, definite, real symmetric bilinear form is an inner product. And a bilinear form is essentially, I'm just going to put that in since I mentioned it. Bilinear form basically comes down to the classic version in Rn is something like f of u and v is u transpose a v, where A is a matrix. But not just any matrix. It will definitely be a there's a word for it. Yeah, real symmetric. And it turns out, yeah, bilinear form is essentially the same as a linear form. You put two vectors in, but when they say bilinear, it means that you can expand it out over plus in either coordinate. So you end up with f of u1 plus u2 of v comes out to f of u1 and v, and f of u2 and v. You can do that. And f of a u1, au and v is a times f of uv. There's probably a thing that says that it's supposed to be the conjugate somewhere. Nope, that's fine. That's wrong. And you can do this in either coordinate. Also in the second coordinate. Yeah, so it's more like, well, bilinear forms are only based on the field that you've got. This is true for inner products here, conjugate symmetricalness. Oh yeah, here. I think that if the field you're thinking about is R, then inner products are done with bilinear forms. But inner products are only bilinear forms if the field you're talking about is R. Yeah. Okay. If the field you're talking about is C, then bilinear forms still do this, but inner products do have conjugation floating around. Yeah. And so that is the vibe. If your field is R, then you will be able to set up your coordinates in such a way that you can always write it this way. If the field is R, then FUV, then, so this doesn't require you to have a matrix first, but you can always find the matrix. If the field is R, then you can still do the same trick. But you have to do everything in terms of a specific basis. All right, I've now filled up all the time. We're going to stop there. Thanks for watching. If you watch that in the future, I'm going to say goodbye now. See ya.